Hello. In this video we are going to conclude our quick survey of Newton's laws of motion by looking at his third law. I think that Newton's third law is his most difficult, but mostly because in the course of my education it was explained to me in some extremely unhelpful ways. I think my problem really comes down to this word action. And so I want to start this video by stating in no uncertain terms that by action I do not mean force. Having understood that action is not force, let's just remind ourselves of the content of my first two videos on Newton's first and second laws. I have thus far argued that physics is our attempt to answer an ancient question on the nature of change. I stated that in physics, we say that change happens when something external to a system acts upon it, and I said that when we use the word system, we mean by this just a part of the universe. I then explained how our first step in developing any physical theory was to characterize the way the system behaves in the absence of any external agent acting upon it to perturb it. In Newtonian physics, this is done by asserting that a body remains at rest, or travelling at a constant speed, unless it is acted upon by an external force. In other words, the momentum characterizes the state of the system, where we use the word state to refer to a behavior that the system will persist in the absence of some external perturbation. I extended upon these ideas in my video on the second law and argued that in Newtonian physics, an external agent applies a force to the system, essentially a push or a pull, and this force causes the system's momentum to change. Lastly, the change in momentum is quantifiable because the force acting on a system is equal to its rate of change of momentum. Furthermore, we can express this sentiment in mathematical symbols using the equation shown at the top of this slide. With all this in mind, let's now take a look at Newton's third law once more and try to work out what we mean by action. An action is something that happens to the system when a force is applied upon it by an external agent. We know what happens to the system when a force is applied to it, however. Its momentum changes. We might therefore rewrite Newton's third law as follows. If the momentum of the system increases, the momentum of the environment must decrease by an equal amount. In other words, Newton's third law is the basis of all our conservation principles in physics. Fantastic! Conservation principles are straightforward to understand, and we should by now have used them to solve all sorts of problems. We'll come back to that in a moment, however. First, let me just take a moment to explain what Newton's third law is not. So at some stage I was given the following explanation. Let's suppose we have a box on a table as shown here. There will be a force acting on this box because of gravity. Why then does the box not fall to the ground? The reason, apparently, is that physics tells us that there is a restoring force applied by the table on the ball that prevents it from falling to the earth. I cannot emphasize this enough. This explanation is complete crap. Force is the rate of change of momentum, and the momentum of this box is not changing, it is stationary. More importantly though, physicists are not insane and are thus not interested in introducing complex theories for the sake of it. We are supposed to believe in Occam's razor. So for any right-thinking physicist, just like for any right-thinking human being, the reason the box does not fall to the ground is obvious. There is a table in the way. Now, you may argue that the kind of thinking about forces does no harm and explains why the gravitational forces in this situation is balanced and so on, but I would disagree. Firstly, this whole notion of balanced forces that we teach children at GCSE is nonsense. If a box is on a table, there is no force acting on it, period. The whole point of introducing force, and of defining it as the rate of change of momentum, is to have a mathematical framework that we can use to explain the changes in momentum that happen to a system, the box, as it moves about. A box on a table is not an interesting problem, and asking children to draw diagrams like this shown here of the force acting on it is, in my view, completely and utterly nonsensical. The momentum of the box is not changing, so there are no forces acting on it, period. Instead of talking about this sort of nonsense, let's solve a real physics problem, like, for example, if we drop a big weight on the table, how heavy does it have to be before the table breaks? That is an interesting problem. The figure here is meant to illustrate another, I think, confusing way in which Newton's third law is discussed. In this way of discussing things, force is defined as a push or a pull, and Newton's third law is introduced by stating that when I kick the ball, I apply a force to it. At the same time, the ball applies a force to my foot that causes my foot to slow down. The explanation here is correct, but really it only makes sense when you know that force is simply the rate of change of momentum. A person, I think, who thinks of a force or a push or a pull is always going to struggle to understand how a ball, an inanimate object, can choose to push a foot when it is kicked. An equally bizarre statement that was given to me when I was taught these sorts of ideas was that when I walk, I push the world backwards, but the world pushes me forward. Again, the problem is that the world is an inanimate object. When I think of the words push or pull, I think of some person or animal pushing something. This is important because in both these cases, some agent has decided to push or pull the object, and decisions like this cannot be taken by inanimate objects. It is thus far better and much clearer to say that when a force, defined as a push or a pull, acts on the system, the momentum of the system either increases or decreases. If the momentum of the system increases, then the total momentum in the environment must decrease by an equal amount. Similarly, if the momentum of the system decreases, the momentum of the environment must increase by an equal amount. My point is that force should only be used to explain this process of transfer of momentum between the system and the environment. The explanation here is tangible. We have all experienced how kicking balls and have felt how the speed at which our leg is moving is decreased after the impact with the ball. In addition, given that the ball will hopefully have flown off our foot and soared into the back of the net, it does not seem unreasonable to suppose that the momentum that our foot had formerly has now been transferred to the ball. Better still, when we see the ball hit the back of the net, we will see the net accelerate outwards and the ball will slow down as it transfers its momentum to the net and thus accelerates it. With all this in mind, let's now introduce a more refined way of thinking about this business of changes of momentum. Imagine, if you will, a sailboat in a hurricane. I will represent the position of the sailboat using this blue dot here. The wind direction and magnitude at each point in a hurricane, meanwhile, is represented by the blue arrows. Whenever the sailor has the wind behind him, he will accelerate and his momentum will increase because the wind applies a force to his boat's sails and thus accelerates the boat. Consequently, because the wind is always behind him as he moves around this circular path, his speed will increase monotonically. That is to say that his speed will always increase and he will never slow down if he moves around this circular path. In most of Newtonian physics, certainly in all the Newtonian physics I do in my research, we deliberately set up the system so that situations like the one shown here does not arise. We can express this condition as follows. If we travel around a circular path, like the one shown here, a path that starts at position A and that finishes at position A, then the value of the momentum, the state of the system, that the system had when we started and were at point A, must equal the value of the momentum when we have finished by returning to position A. In other words, if we calculate the total change in momentum that occurs as the system moves from state A to state A again, we find that the total change in momentum is equal to 0. We can write this condition as follows. We use the delta here to indicate that we have moved. We use the A right arrowed A to indicate that we have moved from position A back to position A. And there is a P because we are interested in the change of momentum, P, that occurs as we take this path. We next recall that the force is equal to the derivative of the momentum with respect to time. We can thus calculate the amount the momentum changes by calculating an integral of the force like the one shown here. In writing this integral, notice that we have written the force, F, as a function of our position in space. We could think of this function that takes as its argument the position in space and which returns the force acting on the system at that point, a vector quantity, in much the same way as we thought about the wind in our boat in a hurricane example. We will thus have a force that will act on each point in space as shown here. These forces will cause the momentum of the system to change. The integral then means that we calculate the total change in momentum that occurs as we travel around the green circular path shown here. Let's now suppose that we want to calculate the total change in momentum that occurs when we move from position A to position B as shown here. We can move between these 2 points in space via a wide range of different paths. For example, we could move along this path shown here. And the total change in momentum as we travel along this path would be given by delta A right arrow B of P. Alternatively, we could move along the path as shown here, which would give rise to a total change in momentum of delta A right arrow P, B, P prime, because this may well be different from the change in momentum that we had when we travelled along the previous path. Now suppose that we travel in a circular path from A via B and back to A again. As we travel to B, we take the path labelled delta AB of P. However, on the return journey, we will take the path labelled delta AB P prime. The total change in momentum during our round trip from A and back to A is thus given by the following expressions. We know, however, that our field of forces is conservative. In other words, we know that the total change in momentum that occurs as we travel around any circular path is equal to 0. Consequently, the left-hand side of this expression is equal to 0, and delta P and delta P prime are thus equal. The change in momentum that is observed in moving from state A to state B thus does not depend on the path taken. In conservative fields, like the one shown on the previous slide, we could thus calculate the total change in momentum that occurs in moving from some start point A to some finishing point B from the positions of the start and end points, only as shown here. To calculate the total change of momentum, we thus do not require any information on the path taken between the 2 points. At the end of the previous slide, I got to the function shown here. I said that the change in momentum that occurs as I move from position A in my conservative vector field to position B could be expressed in terms of a scalar-valued function u that has as its argument my position in space. This is obviously bullshit, as the momentum is a vector quantity and a difference between 2 vectors cannot be expressed as a difference between 2 scalars, or 2 scalar-valued functions for that matter. Please don't stop the video at this point, however, as we are going to do something that makes sense and that should be more familiar in a moment. The problem is that by this symbol delta A right arrow BP, I don't actually mean calculate the change in momentum that occurs as we move from point A to point B. What I mean is calculate the difference in momentum that occurs in moving from point A to point B, and make sure it is a scalar quantity rather than a vector quantity. I can do this by calculating the indefinite integral shown here. The equation now makes a lot more sense. Furthermore, the whole thing is just a statement of the fundamental theorem of calculus. The u function on the right-hand side is just the antiderivative of the force f of x. The next step is to remember that we have defined force as the rate of change of momentum. In other words, force is just dp by dt. So we can rewrite the integral on the left-hand side as shown here on the extreme right. Rearranging these terms in the integrand, we then get to the following. Now, dx by dt is just the rate of change of our position of time. In other words, this is the velocity. We can calculate the velocity by dividing the momentum by the mass. We can thus write the integral on the right-hand side of this equation as follows. Better still, we can now actually calculate this integral, and we can get something that should be very familiar. The function u is just the kinetic energy, and u of b minus u of a is just the change in kinetic energy that occurs in moving from point A to point B. This is definitely a scalar. What is the point of all this, though, and where am I trying to get to? Well, remember that we are talking about Newton's third law, which we have explained states that if the momentum of the system increases, the momentum of the environment must decrease by an equal amount. The problem with this statement of the law is that we have to keep track of the momentum, which is a vector. Let's suppose that we have a system composed of n atoms, and this is in contact with the universe, which contains m atoms. Keeping track of the momentum of all these atoms will mean keeping tabs on a vector with 3, x, y, z, times n, plus 3 times n components. We will thus be required to make sure that the sum of all the magnitudes of all these components remains the same at all times, which, as I'm sure you can imagine, is a massive pain in the arse if m and m are large numbers. In a moment, we are going to find a way to opt out of this insanity for the sake of an easy life. But let's follow the logic through for a moment and evaluate the kinetic energy of the atoms in the system and the atoms in the environment. The kinetic energy of the atoms in the system is given by the formula shown here. The first sum runs over the n atoms of which the system is composed. The mi represents the mass of atom I, and the pi of alpha are the x, y, and z components of atom I's momentum. The function for the total kinetic energy of the system is not too onerous to calculate, as we are generally going to work with systems with relatively small numbers of atoms. If you want to impress your friends with your extensive physics vocabulary, then first of all you have friends who are far too easily impressed. Seriously though, instead of talking about the numbers of atoms, you can talk about the numbers of degrees of freedom in the system. In this case, the number of degrees of freedom is just 3n. Now suppose that we want to write a similar expression for the total kinetic energy of the atoms in the environment. This is much more difficult to evaluate, as the total number of atoms in the universe, m, is very large. For the time being, however, we will write an expression regardless, and we'll see that it is the same as the expression that we wrote for the system. Now suppose that we're interested in a change in the state of the system that occurs as we move from state A to state B. Remember, this does not mean that the system moves between 2 points in space, A and B. The system can move between 2 points in space with a constant momentum, and its state, the momentum, will not change. The key requirement here is that in moving from state A to state B, the momentum of the system has changed. Now, because the momentum of the system changes, the total kinetic energy of the system must also change. Let's say it increases. Newton's third law tells us that as a consequence, the total kinetic energy of the atoms in the environment must decrease, because if the momentum of the system increases, the momentum of the environment must decrease by an equal and opposite amount. Once we introduce one final trick, we are there. This trick involves simply not calculating the total kinetic energy for the environment. We instead state that the total kinetic energy in the environment is a function of the system's position in space. We can do this by noting how the kinetic energy of the degrees of freedom in the system changes as we move about the space, because we know that the kinetic energy of the degrees of freedom in the environment will change by an equal and opposite amount. Putting all this another way, if we find that the change in momentum in moving from point A to point B is given by delta p, this is truly a vector quantity now, then we can work out the corresponding change in the kinetic energy of the system. It's given by this expression here. The momentum that has entered or left the system must have come from the environment or must have been transferred to the environment. We can thus express the change in potential in moving between position A and position B as shown here. Before we move on to the final step, let me just stress the deltas here. Whenever we talk about the potential, we are always referring to a change in potential that occurs in moving from some initial position to some final position. This is often not written explicitly, and you will just see the symbol V without a delta. There must be some reference state, however, and understanding what the reference state is often important. Returning to the problem in hand, let's calculate the rate of change of V with respect to x. In other words, let's calculate dV by dx. It is easy to show, using the chain rule, that this is given by P over m minus P over m multiplied by dP by dx. Remember now that momentum is just mass times velocity, and that velocity is the derivative of the position with respect to time. We can thus write the following. In this expression, the m's cancel, as do the factors of dx in the numerator and denominator. We are thus left with minus dP by dt, which is just minus the force. We thus arrive at the following expression. Force is equal to minus the first derivative of the potential with respect to position. This expression is brilliant as it allows us to use any differentiable function of the positions as the potential that couples the system with its environment, the rest of the universe. We can then differentiate our imagined potential, and we have forces that we can use to work out how our system's positions and momentums will evolve in time. This procedure is so useful that we even use it in places where we could, if we weren't so lazy, quite easily keep track of the momentums of all the atoms. For example, consider two balls connected by a spring. We will imagine that the system is fixed somehow so that it does not rotate. There are thus 2 degrees of freedom for this system, the position of the first ball, x1, and the position of the second ball, x2. Now suppose that the momentum of the first ball increases by delta p1 as shown here. We know from Newton's third law that the momentum of the second ball must change by an equal and opposite amount. So we may write that delta p2 equals minus delta p1. This is not the way that physicists would normally tackle this sort of problem, however. What we would do instead is write a potential that is a function of the distance between the two balls, as shown here. We would then think in terms of the rate of change of momentum for the vector connecting the two balls. This is a rather confusing statement, but the important point to note is that we have gone from a two-dimensional vector of momentum coordinates, a momentum coordinate for ball 1 and a momentum coordinate for ball 2, to a one-dimensional vector of momentum coordinates. We have thus relegated one of the degrees of freedom, one of the momentum coordinates, of the original two-ball system to the environment. As you are no doubt aware, we can think of the oscillations in the distance between the two balls in the same way we think about the green ball shown here rolling about on the potential. We know that the ball's velocity will be maximal when it reaches the bottom of the valley, and that it will be 0 at the highest point that it can get to on the curve. We further know that this oscillatory behavior will continue forever without stopping, at variance with what I have shown in the movie. What we now hopefully appreciate a bit better is how the exchange between kinetic and potential energy that we learnt about during GCSE and A-level, and that happens in problems like this one, is just the physicist's accounting trick to assure that no momentum is lost as it is exchanged between the system and its environment. To summarise then, in all these videos we have argued that physics is about the nature of change. We said that change is that caused by an external agent, and that in Newtonian physics this external agent applies a force to the system and consequently changes the momentum of the particles within it. In this video, we have added in Newton's third law, which tells us that if the total momentum of the system increases, then the total momentum of the environment must decrease. More importantly, however, we've introduced the physicists' accounting trick, the potential, which allows us to keep track of the environment without any need to monitor the momentum of the enormous number of atoms of which it is composed. We have explained how the system is coupled to its environment through a potential, and how Newton's third law thus changes into a requirement that the sum of the potential energy, which is a function of the system's position, and the kinetic energy, which is a function of the system's momentum, remains constant. In this new way of thinking, any external agent, an agent which can affect the system in ways not described by the potential, changes the behavior of the system by changing its total energy. That is to say, it changes the sum of the system's kinetic and potential energy. Thank you for your attention.